Important characteristic, important parameter of a PN junction is the junction capacitance. We know that capacitance is, we said, separate, accumulation of separate charges with a slight separation between them forms a capacitor. Right? When oppositely charged layers, they are brought closer together, they increase the capacity of that setup to store charge. Right? So here in a PN junction, we said that because of the diffusion, the depletion region is found. Yes. From P side, holes move to the N side, they try to move to the N side, and from N side, electrons try to move to the P side, and therefore they ionize atoms that are residing or lying on the junction between the two type of material. Right? If that is P type material and that is an N type material, suppose that this is a metallurgical junction. So electrons move because of diffusion, electrons will move to this side. Yes, sir. Because electrons are in high quantity here, high number here, so electrons will move here, right? Yes, sir. Making this side is negative and leaving this side is positive. Or we can alternately say that holes can move to the other side and making that side positive and this side leaving as negative. Yes. Right? So this here is a storage of charge. Oppositely charged particles or whatever you can call charges separated by a small distance close to each other. This actually is kind of a capacitor. Because you know what is the role of a capacitor? It actually stores, right? If we have we have two plates. If we have two plates and they are close to each other, right? Yes, sir. And you attach them to a potential difference. This side will become positive and this side will become negative, right? And we can measure the capacitance of a capacitor. The capacitance of how much charge, how much charge per unit potential difference can it store. It's called the capacitance of the capacitor. So here there is different doping environment. You know, each PN junction may have different concentration of the impurity atoms. Yes. Right. So this density of these charges may be different depending upon those impurity atoms. and depending upon the property of the material, and depending upon the temperature as well, how much particles can diffuse, how easy for the particle it is to diffuse to the other side. कितना आसान है particles के लिए कि वो diffuse करें, right? So this depletion region can be supposed to be acting like a capacitor. The depletion region. This is also called the space charge regions are the depletion region. This can be considered as a capacitor. Can be considered as a capacitor, right? So, if we have this situation, it reverse bias right? In the reverse bias situation, that's N is attached to positive and P to negative, right? Suppose we have a potential applied to it, and that is VR. And let us increase V to VR plus some dVR. Let us increase the reverse bias. And we know that when we increase the reverse bias, we said the width was proportional to the reverse biasing linearly. I know both are in the numerator, so there is a linear proportionality between. You know, with the square root as well, there is 1/2 power. So when we increase the reverse biasing, the voltage, the width will also increase. So the new width could be like this thing. Because of this reverse biasing, the junction width will increase as our previous knowledge, right? And we say more charges will develop. Suppose that charge is GQ prime, right? More charge will develop over here, and more negative charge develops over here on the other side. If we say, right, if we write this as graphically, and if this axis is the charge density rho, right, then we can say that here roughly on this side is plus E and D. Here the charge density is the electron and the donor concentration, right? And here, you know, it is before, suppose it is before they apply the reverse voltage, so we call it Xn, right? And here there will be a negative. This is I'm writing here a graphical sketch. So that will be like from here to minus E N A, right? And we call this minus XP if you remember. So if the reverse bias is applied, then the depletion region will extend to this level. And so then we can say, let the charge here is dq prime, and the width here, the change in width, I can call it dxn. So the width increases, like this will be like here to here, dxp. So this is the wet at the reverse bias. WHVR, and here now the width is this one, right? And that will be W at VR plus GVR. Now we know the change in capacitance. How much will be the change in capacitance? Change in capacitance, right? We call it C prime. That will be dq prime, right? Divided by dV. The change in the reverse voltage, right? We know that the capacitance is equal to Q by V. Okay, what is the total charge equal to? We know that the total charge dq prime will be equal to E and G, right? And multiplied by Xn. You know, that is the charge per unit volume. That is the amount of each charge. And that is the length. So this will actually be the charge per unit area. Charge per unit. Right. So here we can write equation, if that is equation number 2. So we can put 2 in 1. So C prime will be equal to E and G, right? And we can say that, look here, that also touch the holy. You see, I forgot one thing. That is GQ, so there will be DXN. DXN, right? Here GQ is equal to DXN. And I can write DXN by dV. That is equation number. So we got the capacitance in terms of the rate of change of the space charge region,
Yes.
with the reverse voltage. The capacitance depends upon what? It depends upon here the rate of change of the extension in the depletion region, the rate of change of extension in the depletion region with the reverse biasing voltage, right? So now we know the value from our previous knowledge. We know the value of Xn. That how does it depend upon the reverse biasing? So
Robert, sir, N type जाती कि न P तब हम जाती.
when the doping is the same.
Same.
When the doping is kind of the same, right? So Xn and Xp will be should be equivalent.
Yes.
But if the doping on one side is more, no आगे से की पर क्या? ची doping ज़्यादा, आगे से की भी extension कम रहती. Doping ज़्यादा, concentration ज़्यादा, no ची आगे वाला charge should be the same on both the sides. dq should be the same.
Yes.
But on one side, if dxn, if nd is high, then the dxn should be small.
To keep that.
Yeah, to keep it constant.
Okay.
See that? Okay. Now at 0 bias, we know that, right? Xn was equal to 2ES VBI divided by E and A over N G. So the power 1 over 2 and 1 over n a plus n d to the power 1 over 2. Right? Now, if you remember, if we apply the here, there's a 1 over 2 sign here as well. If we apply some HVR xn, right, will be equal to 2 ES and VBI plus VR. Instead of VBI, now we write VBI plus VR. Say that confirm.
Yes, sir.
Divided by E to the power 1 over 2, right? And A over and Z 1 over 2 and 1 over and A plus and D to the power 1 over 2. If that is equation number 4, right? So I can now differentiate this, right? I can differentiate equation number 4. So 4 in 3 and rearrangement. Rearrangement. So 1 over E and D, C prime will be equal to D by dVr, right? 2 ES VBI plus VR. धातु किसा हो गया क्या हो गया? सही? And A and G 1 over 2 and this power 1 over 2. Right? So when we differentiate that, we get again this thing 2 ES NA or ND, right? To the power 1 over 2, and D and NA have nothing to do with it, and 1 over NA plus N D to the power 1 over 2, and now differentiate the down over 2 pi a go yeah. So when I differentiate this with respect to dVr, I would say 1 over 2, right? VB by plus VR to the power minus 1, right? So when you write it like this, that two system of Yahoo, and I can write this as 1 over 2 and VBI plus VR 1 over 2. Now the capacitance will be equal to now the capacitance, I will write C prime is equal to E as in A and D, right, over 2 VBI plus VR and NA plus ND. That is junction capacitance, and we look, the capacitance is kind of inversely proportional to square root of VR, right? So we said that the charge is if you multiply it with xn q or whatever, that was charge per unit area. So this will be capacitance per unit area kind of. So it should be like farad per centimeter square. This capacitance should be like farad per centimeter square. Let's do an example, right? If we are, the reverse biasing is 5 volts, NA is equal to 10 to the power 16 per centimeter cube, and ND equal to 10 to the power 15 per centimeter cube, and ES equal to 11.7 and 8.85 and 10 to the power minus 14. Then C prime power n, right? So that will be equal to 1.6 10 to the power minus 19 and 11.7, 8.85 10 to the power minus 14, 10 to the power 16 and 10 to the power 15 divided by 2, 0.365 plus 5 and 10 to the power 16 plus 10 to the power 15 and to the power 1 over 2. Right? So this gives us the value 3.66 and 10 to the power minus 9 farad per centimeter square. If area is equal to 10 to the power minus 4 centimeter square, then C capacitance will be equal to C prime multiplied by A. And that will be equal to 0.366 picofarad. So the capacitance of the PN junctions with these characteristics, where this is the built-in potential, this is what? VBI. So the capacitance of a PN junction, of a typical PN junction, with these characteristics, and if you apply a reverse bias of 5 volts, it will be like 0.366 picofarad. Okay, let us think of another uh, type of a PN junction, right? The one-sided PN junction. One-sided PN junction, right? In which one side is doped very heavily. One side is doped very heavily is compared with the other side. Suppose P side is doped very heavily, then we can call the P plus N junction, right? And one side is doped very heavily is compared with the other side. So, as you ask the question, right? Right? They are the GQ or Q was equal to E and A should be right? Or ND and X P we said. So if this is very hard, and the look that will be like the negative, positive, right? On the XP side, it will be negatively charged, right? That is P and that is that. So electrons will come here. So here you can put a minus sign something if you want. And Q like positive, it will be like E, right? And G of X and. So look, for a capacitor, both the capacitors should be equal to each other. Both the charges should be equal to each other. Znači da equal show, or da division hide, no, XP should be very small. When XP is very small as compared with the XN, we call it a one-sided junction. The W will be nearly equal to XN. W is generally equal to XP plus XN. But here, since XP is very small as compared to XN, then we will write W is nearly equal to, right? XN. We know that W is equal to, right? W is equal to 2 epsilon S VBI plus V R or E and NA plus NG or NA and G whole to the power 2. Right? That is the weight of a P-N junction. Now for P plus N junction, NA should be very greater than ND.
Yes.
Which NA very greater than ND. This can be replaced by ND.
Yes. Exactly.
Right? So we can write W is equal to this thing,
Yes, sir. And
right? And NG or no, NA,
1 hour and
NA or NA and NG to the power 1 over 2 and to the power 1 over 2. Right?
yes, sir.
R, this NA goes with an A, so it can be, W can be written as 2 ES VDI plus VR and over E and G to the power 1 over 2. Right? Now, as we said here, xn should be very large as compared with xp. Right? Here, xn should be very large as compared with xp, and w can be written as xn. सही रहेगा ना? It could be like this. मसलन जो ग्राफ को ड्रा करो ग्राफ. The axis one is open. They want a density, you can charge density.
Yes, sir.
सही है? Now minus should have plus show. और उधर से भी मसला x show. No x and master first kadal kare, right? Or master I have NG very small as compared with NA. No master badasi the same charge for master raki or dumra both side. Right?
Yes.
Q, this will be Q plus side, right? Q plus side, which is equal to a larger xn and small nd, right? And to this side, it will be a small xp right? Then this is plus nd, I will call it E and D, plus charge on the side. Here on this side, charge is negative. And there will be minus E and A. Right? So XP will be this one. So this kind of junction is a one-sided junction. Now there is a benefit of the measuring the capacitance of a one-sided junction. That is function you register. C prime will be equal to E S and A and D and 2 VBI plus VR and A plus ND to the power 1 over 2. That is the capacitance. So far, a one-sided junction in which Na is very greater than Nd, right? That can be approximately taken as Na. Now Na goes with Na, and the new capacitance will be EAS ND by 2 VBI plus VR C prime C prime C prime, right? And to the power 1 over 2. This is suppose equation number 3. Now you are measuring capacitance. 1 over C prime. If you when I was at Kailasam University, we used to use this formula for measuring the capacitance of a junction. We would use measure the capacitance of a junction and the temperature dependence of it. You know, we were using liquid nitrogen, and we would slowly raise the sample, the PN junction, above and there would be liquid nitrogen in a thermos. You know, and we would slightly raise our sample slowly, right? And would note the junction of the capacitance. And we would measure it as a function of temperature as well. So 1 over C, if you invert it, if you divide 1 with your measurement C, 1 over C square, right? And you take the square of it, you get this thing, 2 VBI plus VR divided by E and ES and G. So if you look at this, right, this is kind of two variables, 1 over C prime square and 2 over ES and D, and this is the variable VI plus VR, while you increase the reverse biasing, right? While you increase the reverse biasing. So look, this is directly proportional to the square of 1 over C prime. You measure C prime, then you take inverse of it and make a square. If you plot these two, then this is like a direct relationship, a straight line relationship, and this is the slope of that. You remember the equation y is equal to mx
Yes, sir. Line
plus c,
Yes,
straight line equation,
Yes.
where m is the slope
Yes, sir.
So, if we plot it, that is equation number, suppose 5, and that is 4, right? So, I'm plotting 1 over c square is compared with VBI plus VR. So, on this axis, I have 1 over c square. Right? So, when VR equal to 0, 1 over c square is not equal to 0. It has some value.
Value, yes.
So, let that is this value. That is VR. If VR is equal to 0,
Yes.
1 over c square has this value.
Some certain value, yes.
It is this one, this place. So there are 2
Divided
VBI divided by
E, ES.
ES and D.
Yes.
It has a capacitance 1 over C of the capacitance, right? Square of that value. Now, when you increase this VR, the capacitance decreases. Look,
Yes.
when you increase VR,
The capacity.
so when the capacitance decreases, 1 over C will
Increase.
increase. So you get a straight line like this
Yes.
when you measure them. Right? And we would call this Arrhenius plot. When you extend this to this side, when you extend this plot, I'm drawing it solid. But when you extend this plot, the VR is equal to 0 shift, no right?
Yes.
That's the extent the built-in potential volume. Look, this plot has an intercept, right? Where the capacitance is like 1 over c square is equal to 0, right? Look here, and this when this crosses this line, when this crosses the x-axis,
Yes.
so at this intercept, 1 over c prime square equal to
0.
side down,
Yes.
and when this is equal to 0, look at this equation. This is not equal to 0 because these are constant values.
Yes.
This is equal to 0, so this means that this must be equal to 0 because this is not equal to 0. So this means that VBI plus VR equal to 0. Or VBI is equal to minus VR in this situation.
Yes.
Right? So the VR that the solution VBI should actually. The VR or the minus VR she must
Yes.
no that's among the built-in potential should measure the graph on the graph. The voltage forward ko bhi na.
Yes.
The reverse bias take na.
Yes, sir.
So then biya forward ko na che forward bias ko. Khatam so measurement zat khatam. Reverse bias 0 and then increasing the reverse bias. We got this line.
Yes.
Now you extrapolate the line by hand.
I see.
Extrapolate this straight line with the same slope, and it cuts this x-axis here.
Yes.
Then you measure this place, which is the built-in potential. So the benefit of this
Yes.
capacitance measurement, you can also find the built-in potential of a p-n junction.
Yes.
So that is x-intercept of the line, right? You are using a certain scale here. 1 volt is equal to
Yes,
one,
sir.
one division or whatever.
Yes.
So from that scale, you will measure this side.
Yes.
Right? The head, it will be the same scale. If this is 1 volt, so 1 volt, 2, 3, 4, 5, 6 are here. 1, 2, 3, 4, 5, 6, 7. Kind of understanding. Like if this is 0.1 volt. So it would be like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. It would be like 0.7 volt will be the built-in potential. You know what I'm saying?
Yes.
So that is one of the uses of measuring capacitance of a p-n junction. Now let us move to the other chapter, the p-n junction diode, and do the junction breakdown.
The x-intercept मतलब x axis को कम line को कम point बनाते हैं
Cut.
करके
यो लाइन चाहिँ x axis पर कम value माने कट कई अगर हर लाइन x intercept और the line चाहिँ y चाहिँ पर कम माने कट कई बता चाहिँ the y intercept है the line y intercept दाल और the line x intercept दाल
yes
the y intercept है और the
x
x intercept. A straight line will cut one axis at only one point. The junction breakdown, right? When you rapidly increase the reverse bias, you increase the reverse bias.
yes
Right? Rapidly increase the reverse bias. Below certain limit, this will give you what? The very high current. This very high current is called junction breakdown. Right? And the voltage is called the breakdown voltage. Hello, Irfan.
So G more
More no,
more
more okay. This is called now junction. There are usually two mechanisms people consider. The breakdown is divided into right? Two categories: Zener breakdown,
and avalanche.
yeah, and
Avalanche.
avalanche breakdown. Zener breakdown. Occurs in very highly doped PN junctions. Very heavily or very highly doped PN junction. Very heavily or very highly doped.
Doped PN.
Look, when we said when the P and the N junctions are very highly doped, ND and NA will be very large. ND and as a result, XN and XP will be very small.
Yes.
XN and
Yes.
XP will be very small. The depletion region will be very thin. Very thin depletion region. Very thin depletion region with W kind of tends to zero or whatever. Right? Not zero, but very small. The width will be.
Very small.
So when you apply, it would be like, that's the P and junction. So that is metallurgical junction. So it will be like something like this one. Look, the building is landing. And that is double. Now when you apply a reverse bias, right? There will be band bending. As in band bending, we cannot. Band bending will be like this. All there is into it, yeah. That's band bending, yeah. The EC to conduction band, or the E, which balance band, E, C, or E, with E. Here, the valence band, the energy of the valence band, right, is higher than the conduction energy on this side. So there are electrons and they can tunnel to the other side of the other side of the junction, right? Like this is a reverse biasing. You have applied the reverse biasing, all right? So the electric field is in this direction.
Sir, the tunneling is to see that we have quantum mechanical behaviors.
Right? So we can think of that in this situation, this barrier is very small. The barrier is small, and the energy here is greater, right, than the energy there. Electrons under reverse field will be attracted to this side, tunneling, through tunneling, from the valence band. Electrons from the valence band can tunnel through the barrier and give rise to high current. Right? This situation is called Zener breakdown. Not very common. Because junctions are not very heavily doped. The other breakdown mechanism is called avalanche breakdown. We will slightly discuss the avalanche breakdown and then we finish it tomorrow or the next day.
سبب class one.
شباب ونعمل وظيفة.
Immediate class of the class is something.
فترة كذا بلغتك بالسؤال. لا بس بس हाँ तो करंट पास इसो अमुंग आला behavior ना तो नहीं करेगा है ये तो अमुंग नहीं तो डायोड ऑफ behavior चले ये करंट अपना नहीं चलेगा
New voltage or
हाँ that's the forward show और अभी ये तो हम IV characteristic और
okay, sir, new voltage or
IV characteristics of a PN junction that's it that current or that's it
voltage.
لا हम ना लेते वो बता दो शो के लिए so avalanche breakdown right so we have to do this do it for us
So बस मिटा होगा ना
lightly doped P and junctions. So here the space charge region is large. Right?
Yes, sir.
Now, when you have applied reverse bias and it is high, greater than the working voltage of a PN junction, this electric field, it attracts, for example, the electrons will move in this side because this is the electric field. So electrons will be attracted to this side. And here, holes will be attracted because of the action of the electric field.
Yes, sir.
So these electrons when come here, they can have enough velocity because of the electric field. And they can ionize atoms and knock out electrons from them. Knock out some electrons from them. And some holes are created as well. That's again atoms holes created. So electrons and hole pairs are created here in this type of breakdown. Due to the high voltage, electron and hole pairs are created because of the motion of some electrons that leak and holes. When they pass through, they ionize the atoms over here. And as a result of the ionization, an electron and a hole is produced. So a hole will be attracted to this side and electron to this side. And it gains further because this is wide. So with the distance it travels, it gets more and more kinetic energy and ionize further atoms in its path. And create an electron and hole pair. And a large amount of current is produced in this phenomenon. Right? This also depends upon temperature, etc. So, if we say this is x is equal to 0, right? And this is like xn, suppose. So, if there is a small current here, that current can increase, when you go to the side, that avalanche current, because of producing the electron hole pairs. Right? So it has a lot of mathematics. So the avalanche breakdown. So let us do it the next day. Okay? And then we will start at the same time, hopefully, we will start the current, PN junction current. And maybe after a couple of lectures it will be done.
Yes, sir.